Good afternoon everyone. This is picking up on lots of little bits of detail that people get wrong with graphs and things. So 4 things I want to cover. How to record the data correctly, to actually make sure it's up to standard. How to get a good graph, how to get a great line of best fits, and as part of that, this quite advanced technique using error bars. So we're going to pick up on that a little bit, but show why it's needed to do. Okay, so I'll record another video on how to get error bars right. Okay, so here we've got some data. It's for one of the classic experiments, a Boyle's law experiment, and what we've got is our results table here. Now, by looking at the results table, I can tell what's being done. The first column is what I changed in the experiment, or what we changed in the experiment. And that is the dependent variable because it depends on what happened in the first place. So always go in that order, what you're changing, then next to it, the reading that you're getting out from your experiment. And I would suggest that you do this twice. This experiment is one of the few we don't because it kind of gums up. But normally, volume 1, volume 2, average volume. Okay, now notice, again, to make it correct, I've got my units in there. It leaves the numbers nice and clear. If I slide that down, got little things to frame it, but you can see the patterns in the numbers and you can check them as you're doing it, because I haven't got units in here, I haven't got times 10 to the whatever. So this is 110,000, but I haven't written 110,000. I've just put 1.1 times 10 to the plus 5 pascals, or newtons per meter squared. Okay, over on my graph I've got exactly the same titles as I got here, so it's nice and clear. Now I have put these the other way round just to show the part of this in more detail. What I should have is my volume depends on the pressure, so my volume would go here, my pressure at the bottom, but you'll see a little bit more easily what's going on. So if I take my data, what I end up with is a curve, and this is one of the difficult ways of getting graphs. My good graph starts with the fact that I've actually filled the page. Okay, so my numbers themselves on the graph go from here all the way down to near the bottom. Okay, so I'm at least half the page. That's well over half the page, and it's definitely pretty much the full width of the page. Now, if you're not sure, look along it. If you look along that data, you can tell if I hold it even steeper, there's no way that that's a straight line. You can see a curve in there. So what we're after is put your head along, look along it, you can see the pattern, and it's going to be somewhere around there. But it's quite hard to get right. Okay? Now, to help you, we're going to use error bars. Okay, so the error bars that we're going to put on come from how precisely we've measured the readings. Okay, now this one you might be able to guess by looking at these, because they're only 0.5 or 0.0, that these are probably about as precise as you could get it. But these values here, well, if we look at the 0.4 for example, we know that actually it could be anywhere down to 1.35 up to 1.495, etc, etc, 9999 even, but I'll say 0.4 because when you round those to one significant figure, one decimal place, 2 significant figures, when you round them up you'll end up with both of them appearing as 1.4. So we have a spread of half of whatever the difference is between these. So this is 1/10 of the unit. Okay, the unit's fairly big, but it's 1/10 of the unit, and so half of 1/10 of the unit, so 0.05, is what you could be up to and still be rounded to that number. Which means that when we're looking at the axes, this point isn't necessarily there. It could be 0.05 above that or below that in pressure. So we can draw that, or we can show that as an error bar, a spread. So on my scale here, that's my 2.7 at the moment. It's the value down at the bottom, just in case you're wondering. So 2.7, but it could be 2.65 or 2.75. Okay, so actually it lies in that spread there. 5 little squares on my scale. Okay, and that is the same for all of these. So what I can do is I can go down all of them and put in a bit of a spread. Okay, not that kind of food spread, but there we go. We can spread by 5 squares, 5 little squares each side of these, around each point. So 2.5 squares above, 2.5 squares below, to give us a range of 5. So if I put all of those on, try and do that roughly, there we go, then what it means is these are the measurement errors or measurement uncertainty in all of our readings. So no matter how good your readings are, how well you've done it, how accurately you've taken it, your readings themselves will actually have a bit of variation, and that means that anywhere within these bars we've got our different values. So what we need to do is that it shows 2 things. One is that no result is perfect. Okay, they've all got a bit of give or take, but it also shows that the results, none of them are any more important than another. They're all slightly wrong in a way. Now I should say we also get a variation in the volume, but on this scale it's a bit awkward, but also I think it's pretty precise. So the squares would be really small, the spread in the volume size would be fairly small. So what I can do is draw a line of best fits. I'm going to do that for a curve. So next tip, if you put your arm on the inside of the curve, I'm going to spread it like that, so that your arm hinges around either your elbow, if it's a really big curve, or around your wrist, and you can get a much smoother version. So if you're not very good at this, or you need a lot more practice, then what you need to do is kind of do a very light line that runs up through, and what you'll find is a bit wrong at the top there, but we can still make it fit very well. So you get it very, a little bit hairy, as they say in the trade, but then draw one and follow that rough curve, one smooth line through the whole lot. Okay, so there we go. We have a line of best fit. It looks pretty smooth, slight lump there, sorry, but it looks pretty smooth, and it goes through every single error bar, because all of those results are good results. They just have a bit of variation. Now, there is another important thing which error bars pick up as well, because they're much more difficult if you do the wrong graph. What do I mean by the wrong graph? Well, if I look at these are the actual readings I've taken. This is our raw data. These are the measurements that I've taken using my measuring instrument. If we plot those directly onto the axis, then what we can do is simply draw on the bars. If we calculate something, so for example if you hung the mass on something and then you calculated weight, well then it's a lot harder to scale the error bars correctly. So it's always a good idea to put on the actual reading that you've measured, okay, your raw data. Maybe your average, because you'd want to have a good one, but it's the actual data that you measured itself, okay, not calculated. Now sometimes you can't get around that, sometimes you have to calculate something. So this graph, for example, is a curve. You can't really get anything from it other than taking readings off, bouncing them down and seeing if we can mathematically relate them. But in this one, what we can often do is we can take those readings and manipulate them. So instead of pressure against volume, I have an idea that this graph shows that if we are doubling the pressure, then we are halving the volume. So it's an inverse curve. It looks like a 1 over x curve. So what I'm going to do is plot 1 over x, or 1 over y. So again, I've kept the volume along the bottom just to make it easier. I've chosen the same scale, but I've calculated 1 over pressure. So instead of 10 to the 5 pascals, it's 10 to the minus 5, because it's now on the bottom, and again it's pascals to the minus 1, because it's underneath the 1. That, if I'm right, gives a nice straight line, and it pretty much looks like it. Okay, so again, error bars I could do to make it easier. I could do that on the volume, but they would be really small, so just remind you that's far too small. These ones are harder because I've done something mathematical to get these values. These are calculated values, and that means that the error bars would actually all be different sizes. Imagine the horror with that. If you're using Excel, you could get the error bars built in and it would do it all automatically for you. Okay, but again, the principle, remember that none of these are exactly right. They're all a bit give or take due to the fact they've been measured. So in terms of my line of best fit here, let's see if I can fit it all on. It's a fair amount of scatter in these results. You can see against my line here there's a lot of zigzagging, particularly up at the top end here, which was actually when you had a really big pressure. So in terms of the experiment that we got this data from, these results are actually slightly dodgy because the pressure is so high. It was causing problems. So ignoring that though, okay, we're not taking that into account, we're just treating all of the data equally. We're looking for a nice even scatter along the length, not at one end but both sides. You're fitting right through the middle, okay, and it doesn't need to go to the origin. I'll be tempted to always leave a gap, okay, maybe put a dotted line at the end or a dashed line, because we don't know what the data is down there, we haven't done it, and in this case it's not the origin anyway. Okay, so don't always try and fit your thing to the corner, it's often wrong. It will be due to other things. But here again, this idea of error bars, you know, if we had them on here and our line happened to fit through all those error bars, that'd be great. But these ones up at the top end, for example, you'd find that if that was your error bar, it doesn't go through, which means this is a bit of an anomaly, not quite correct, and possibly some of the others. Again, why? Because there's problems with the actual experiment at this stage. It's not about the measurement, it's the quality of the measurement that you took. So it's not how well you measured it, but it's actually something causing the measurement to be a bit off. Okay, so overall pretty good data because they're all pretty close to the line, less so up here. You could possibly guess that from the curve, but it's really hard to. But you can tell effectively once you got your line in anyway from your error bars, you can see how far they are off. That one looks a bit of a dodgy result. This one again at this end, they're a bit harder to see, so these are actually the dodgy pressures at the top end. But again, several key things then. Tables drawn correctly, nice and neat, simple, clutter free, so you can see the numbers really easy. You can see the patterns increasing and decreasing steadily, so you can check for dodgy results. Same titles as what you've got on your axes, okay, on both sides. If you can put in that idea of error bars, then horizontally and vertically, or definitely on the one which is the biggest uncertainty, the ones that are least certain, so in this case pressure, so your variation in pressure. and then draw your line or curve of best fit through as many of those as possible in a smooth curve or a smooth straight line. Okay, and you end up with that little scatter each side. So great line of best fits, a good graph, nice and big, filling the page, much easier to get a really good accurate value for. So in this case, to round it off, I can now turn this into an equation. Okay, and from my equation I can find the gradient and the constant in the equation that we're going to use. Okay, so lots and lots and lots of really simple but really important techniques to use with graphs. Okay, thank you very much, guys.